it was completed December 2019, so last year. The client was Liverpool City Council. The client's project managers was Amy, and they also had a principal designer role, and Graham with the principal contractor. Sam Evans were working with them. We were working for Sam Evans, as were Sarens and Core-Cut. Core-Cut did the cutting, the cutting of all the concrete. We also had a couple of other people in there. You've got Rambo, who did the Cat 3 check on the structure and the analysis of the structure and the assessment undertaken as part of the AIP. And then the temporary works were Cat 3 checked by Andun Consulting Engineers. So there was two AIPs submitted on the scheme, one for the assessment of the structure, and one for the design of all the temporary works, which was done to Eurocode, because that's the way the council and Amy pushed us to go. So that's what we did. There's also other people involved, such as traffic management and the like, but I don't know where you stop with bringing people in. This video here gives a bit of an insight into the site itself. It's going to show some of the key constraints. So the first one is the Mersey Tunnel there. And this is the South Flyover. We're working our way along here. Obviously, none of this is here now. This is history and will no longer be in the Google Maps. That's the Liverpool Museum. And then there's a footbridge you see underneath there, which also came out as part of the works. And now we're panning along the North Flyover, which was fairly straight. There's a slight curve to it, but pretty much straight. You've got a university building there. And then you've got some of the constraints here. So there's houses and also university buildings very, very close to the flyover itself. As you can see, it's a very tight, constricted city centre with busy roads all around it. What you can't see on there is there's also a railway underneath it, a railway tunnel. Not that really limited the works, but it's there as well. It's also something else that had to be considered. I think Jordan's going to touch on the logistical challenges of planning this in this city centre environment in his presentation, so I'm not going to go into that too much here. This is a video that kind of sets the scene, and it's much easier to explain this project once you've seen this video and you've got more of an understanding of what it is we were doing and what we were trying to achieve. So I'll let you sit and watch this and maybe talk over bits of it. So there's the SPMTs, self-propelled modular transporters that Sarens provided, that Tom will be talking about. There's a machine giving a little bit of a tap up there to release a section, I think. Some of the temporary propping going in place there. That's the mid-span propping. That's Core-Cut doing their thing. Sam Evans cutting up some barriers to release the sections, and that's a dynamite saw. For those of you that aren't aware, you see it in action there, ripping through the concrete. So we're physically cutting it into sections there. Sections that sit on the SPMT. And there's a cut completing. A nice little separation line. SPMT doing its thing, moving a big heavy load, and some of these lumps were 650 tonnes we were moving around. I think the lightest was about 400 tonnes from memory, wasn't it?
350.
350.
Yeah.
That's the first section coming out there, sitting on the SPMT. And that's the SAR lift that's going underneath there. Again, Tom will talk through the Sarens kit and the bits and pieces that they specialise in. And this is one of the pieces after it's been cut up, ready to be shipped off site on the back of a wagon. It's been loaded up, strapped down, and away it goes to a site just outside Liverpool where it was then processed. I think it's all processed into 6F2, wasn't it?
Yep.
And then the mechanical demo, which we did for the final 4 spans on both viaducts. I always think they should have taken the after video a little bit later than they did, when there wasn't a pile of scrap sitting there, but you get the idea. You can see a section sitting there, and the change it's made to the area is quite spectacular. Okay. So restrictions that were in place other than the physical ones that we've just looked at, the timescales. So I don't know, we probably looked at this for about 18 months, didn't we, Jordan? or about a year before got going?
I mean, we looked at it, yeah, probably about 18 months. The first 12 months, though, we didn't really have much meat to the bone, and it was kind of design your own scheme. And then probably about 6 months before they started to ramp things up and start putting some restrictions in place from the council, etc. Original programme, though, we looked at starting, well, originally one started in the summer due to the neighbouring universities, but obviously that didn't happen. But original programme, I think, was about 7 or 8 months. Yeah. But some of the hierarchy at the council decided to publicly announce that it'd be done by Christmas, so we have to tighten our timescales and get it down by December.
I think we had under 3 months to go from scheme to final approved engineering package for us and for Sarens, and then you had about
I think it was 6 weeks for us.
Sorry?
It was about 6 weeks when we finally got into it.
By the time you got your order.
Yeah.
Yeah, it wasn't very long at all to try and do what we did. Another big constraint, it was noise and dust. That kind of drove the initial methodology completely, given where it was. The council placed very strict noise restrictions and dust restrictions. And in fact, we actually did some on-site testing, didn't we, of different bits of plant to show the sort of noise we could expect to get permission. There's some statues around. There was trees and also nesting birds, which caused a few problems with, or potential problems. There was obviously the roads as well. We had to keep the roads open as much as we possibly could, particularly for buses as well. It's quite a busy area, that, for traffic, and that really did drive the possessions. And we had, was it like 3 or 4 road closures was all we had to do the works.
Yeah, we had 4 road closures in total. 2 of them were designated to the footbridge demolition, and then 2 to the actual removal of the main structure.
We also had pedestrians with the university building there. There's a lot of pedestrians in the area that we had to maintain pedestrian flow. Site investigation, there was a lot of it on the structures, but there was no as-built or record drawings of the northern flyover at all, which complicated things somewhat. And we couldn't really do any more site investigation given the time constraints and the sort of TM restrictions that were in place that we would have needed to actually do the investigation. So it complicated things somewhat. Oh, I'll skip 2. Here we go. Yeah, skip 2. So if you're looking at the picture there, you've got the footbridge underneath, and then above that you've got the flyover itself. So this is a picture of the north one, and just here is the footbridge there, and that's the footbridge, and then that's the flyover up there. So the flyover is about 10 metres wide, up to 12 metres in height overall. The ground falls across the site, so you've got varying heights. Generally, well, always 1.5 metre diameter RC columns, and there were a pair of fixed columns in the centre, and the rest of them sit on longitudinal roller bearings that allowed the whole bridge to expand and contract with temperature variation, which posed some stability issues given the methodology. So if you think back to the video, we were slicing it into pieces, leaving the columns there. So those columns then had to be held in place when we cut either side of them, because they just sat on a longitudinal bearing, a roller bearing. The structure was also post-tensioned, fairly typical of the time. Big, long span post-tension structures was the thing to do, and they got fairly good at designing these structures. The question is always, with post-tension structures, are the tendons bonded or are they not bonded? So the tendon itself is made up of a series of, some forms of post-tensioning are made up of a series of individual strands there, which are then tensioned. In this case, I think we had something like 4,000 ton compression force placed across the section. Once that's done, the whole thing gets grouted, or it doesn't get grouted. If it's grouted, you then lock the stresses into the structure and you can slice through the tendon pretty much as you like. If it's not grouted and you slice through the tendon, then you can get a huge stress release, a really huge stress release, and you've obviously got to be wary of that. Now, the SI that was undertaken on this project indicated that everywhere they'd looked at a duct, which is the tube that surrounds the tendons, they'd found it fully grouted and the tendons themselves were in good condition, which gave us confidence that we could slice it into pieces exactly as we did. Now, if it had been ungrouted, then it would have been a completely different question as to how we took this structure down. It would have made our life far, far trickier than it did. Now, with post-tension structures, you've got to think about how these things were built. So if you look at the excerpt here from an original drawing, if that's one span, they cast from that column support to just past the column support to the point of contraflexion in the bending moment. And at that point there, you anchored the tendon. So that's the wire, the profile of the wire there was anchored at this point. Stressed up, grouted, and then you cast the next section and you repeat. Now, this was one of the earliest structures where instead of having two dead anchorages or two anchorages, they tied the next tendon here onto the previous tendon here. So that it was all tied together in one. Now, given it was grouted, this wasn't too much of a problem, but you've got to keep in mind we had to consider what if it's not grouted throughout, if these anchorages don't work as we want. Given the environment, we had structure that was sitting over a live road. So there's an awful lot of thought and risk assessment that went into the development of this scheme and ensuring that what we had was a safe, workable scheme with sufficient controls in place if one of our assumptions was incorrect. So as part of that, there was a series of drawings that showed the logic behind the engineering and the analysis that we were undertaking to justify how it would work. So we introduced these propping systems. So one of the key failures that we identified was a shear failure. Now, if you imagine that we cut through and remove this section here, just here, where that blue piece is, you've got the tendon has got to re-anchor itself in that crosshead. So what I mean by re-anchor is the tendon has got to create or maintain a bond between the duct and the tendon itself here. Now, as soon as you cut something that's under a high stress, which those bars are, it will expand slightly. That's what locked it into place, and that's what locked it in to the crosshead there, and that maintains the post tension across that section. Now, if, for instance, it didn't re-anchor in that length, you could have ended up with a lack of compression or pre-stress across that joint there, which would have shown shear failure, the most likely failure mechanism. An axial load on concrete vastly increases the shear capacity. And if that had been lost, we had the potential for shear failure, which is a sudden failure without any real warning. So we identified this shear prop solution here, which would sit there, and if it did shear, it would pick up and sit down on that prop. The next mechanism that was potentially identified was, what if we lose anchorage across the whole length there? So what if, for some reason, one of these spans hasn't been grouted up, or it's been missed in the SI, and there's no grout in one of them. And when we cut through here, we lose the tendon all the way across that span. Then you've got a shear problem potentially, plus you've got a bending problem, because that deck won't span from there to there without the post tension operation. So these central props were introduced in the middle here. That meant that should we get a failure here of the post tension, it would be able to sit down quite happily. Now, this then caused the problem of how do we get that section out if the post tensioning fails, which is where the next headache occurs. Is you've then got to detail the propping system to be in place while the SPMTs are able to get into place, which I'll talk about in a bit later on. But whenever you thought you'd solved a problem, you found another problem on this scheme, and it just kept on going like that. It was quite a challenging one. Also talked earlier about the stability of these piers. You can see this propping arrangement here as well. Monitoring was put in place throughout the works as well to give us an indication of whether the post tensioning was failing. I think we had about 2 millimeters movement was the worst case that was picked up during any of this. It was grouted and it remained bonded throughout the tendons. There's absolutely no issues at all with the behaviour of the structure. It went as well as we could possibly hope, really. Excuse me. But we had all these systems in place to make sure that the structure behaved as we expected it to. So the structures themselves, the south viaduct had spans varying from 15 to 33 metres, about 260 metres overall length. The central pier here is the fixed pier. So expansion occurred from the middle point out and from the middle point out that way as well. All the other piers were on roller bearings. Similarly, up on the abutment here and the abutment here, you had roller bearings as well. So the whole structure could move with heat variations throughout the year. Now, the sequence itself, it changed a few times during the life of the project. Realistically, we would have preferred to have worked towards the fixed pier that we talked about here, because you're maintaining the stability of the structure. The way we were forced to go in the end was we had to take out 2 spans here, and then we took out either side of the fixed pier. Now, that was driven by the principal designer's fear of having this structure over a live road during the demolition. So we were kind of backed into a corner, but that's what we did. So the actual removal mechanism was NK and NJ, which is the most westerly sections. Then we took out the piers, the sections over the road, and then we took out the 2 that were kind of next to them. And then we did a similar process on the south, except we started over the main road and worked our way back out. Excuse me, something in my throat this morning, sorry. The first 2 spans were taken out at the same time due to program, and we had the kit on site, and it worked out with the overall logistical sequence. So put the SPMTs underneath, jack them up to, I think we said 80% in the end, didn't we, of the expected load, and then start saw cutting our way through. And we kept the saw cuts in tandem, so both released at the same time or as near as we could. You can see the propping in place adjacent to it. So the central propping, the bending propping, and the shear propping there. In the risk process, we didn't believe we needed to prop the adjacent span based on our analysis. So we propped 1 span adjacent to the sections being cut. Now the propping itself, I mentioned, was driven by the requirements to get the SPMTs into place. You'll see in a later slide that you end up with, let me get a pen, let me draw here. You end up with an SPMT here. I should have used Sarens blue, really, shouldn't I, Tom? Let's change to Sarens blue. And there. So this propping system was arranged so we could get the SPMTs in either side, and still have this propping in place. So should the post tension have failed, we could bring the SPMTs in. It would have been a bit more faffing around because we'd have had to put the steelwork in place underneath the bridge. But that's why the propping was done in this form, and the shape of the rakers, etc., was all designed to make sure we could get all the Sarens steelwork in place whilst maintaining support to the structure. You can see in plan where it all sits. There was a 3D laser scan undertaken of the entire site, which was really, really quite helpful for laying out the temporary works. It meant we could pull a section at every point where we were going to prop, and every point where the SPMTs were going to sit, and etc., etc. And we could then share that information with Sarens on makeup of each prop. A proposed platform level it allowed Sarens to understand the falls that were on the site, cross falls as well, and allowed us to plan and propose working platforms and the levels for the working platforms to make sure the whole system worked. And it gets really quite critical. You've got a limited stroke on the SPMTs, and there's only certain slopes they can go up, which I'm sure Tom's going to talk to you about shortly, especially when you bear in mind you've got a 500-ton lump of concrete 12 metres in the air. You can't be going up too many steep slopes. That's why. Right. So the central props were pretty much placed in the middle there, and then that would allow the SPMTs to come in here. Let's sit here, and then all their steelwork that sits on top of them to come in here like this. And it just allowed the whole system to work. I have to press back on that now. I'm having some IT issues today. Is all of that drawing still on your screen?
It is, yeah.
Yeah.
Right, there we go. So the props themselves were based on a proprietary piece of kit that Sam Evans already owned, which was these tubular props here. These were adapted with the rakers and then these big crossheads. And then the stalls themselves, so these stalls were detailed to allow us to use them pretty much anywhere on the site. And as you recall, this structure falls, and it's got cross falls on it and longitudinal falls, and then the ground slopes. So you have to come up with a system that was flexible, that allowed this packing here to be adjusted for each location. And we actually did tables and drawings that showed the makeup for each of these locations. As it turns out, the site team, instead of putting the packing here, it was much easier on site to put it on top of this. So it was a lesson learned for the future. And it was actually preferable to, instead to have to bolt through each of these, they put them on top and they had the site welding, and they just tacked them all together. And that turned out to be the simplest solution for all. So certainly a lesson learned for us. There is the propping in place, so you can see the shear prop there and the middle and the central props there. You'll notice that these are made of a pair of beams and this is a single beam. The shear prop, if it was loaded, would end up with a much greater load than these pair here. So this was quite a lot heavier fabrication. That's obviously replacing the capacity that concrete pier has. So it was quite a lumpy prop that.
Yeah, just the top half from the tubular prop and the top beam was 8.5 ton.
Yeah, I bet it was a big old lump. And the reason it picks up on these 4 points here is within the structure there's 4 webs, and it was under those we were picking up. So that's why you've got like the 4 stalls there. So it's to try and maintain the support in the best way we could. The columns themselves, we had to prop these to stop them falling over. If you've got a 12 metre high column sitting on roller bearings and it's got a 50-60 ton lump of concrete at the top of it, it's not the most stable thing in the world. So this propping solution was devised, and this also had to be devised again to allow the SPMT to get in and out. So that's why you've got this propping arrangement with the rakers back down that side and a steel that extends this way. This would keep the system stable if it was trying to rotate in any direction, but still allowed the SPMT to travel in this way. Again, it was all, there was a lot of tight clearances on this job. When you start playing with the SPMTs, they're big old lumps and the space soon disappears. So you can see one in place there. You can see this is actually a different form of propping that was used when we ended up doing mechanical demo, which we'll touch on later. So you can see there's 4 webs, 1, 2, 3, 4. So that's the points at which our props are picking up. It might not look like it in that picture, but it is. What was interesting about this is a lot of these bridge sections that came out still had the original timber formwork within them. So they built timber formwork and it just all been left behind in there. There's also quite a few places where the formwork had blown out. So this had been picked up in the SI undertaken by Amy. So we'd all agreed we'd have an additional allowance on the weights, the calculated weights, to make up for the fact that we knew there were areas where the formwork had blown out, to account for this additional load. Some quite interesting papers available, I-Struct-T papers from the time when these were built, and it was quite heavily unionised. So there was quite a few issues where the site team walked off at the end of their shift, whether they'd finished the concrete pour or not. So there was some concerns about the quality of the construction, but from generally what I saw on site, it wasn't too bad, the condition. You're going to add something then, Jordan?
No, there's a couple of bottles of Guinness in the voids as well.
Was there?
Yeah.
Nice. So you can imagine there, if that was standing up and you cut out the span on the other side, you'd want something down here to maintain the stability of the structure. And again, you can see the clearances are quite tight to the site extents and the roads we have around us here. Now, the saw cutting itself had to be planned out for a number of reasons. The first one being the crossheads themselves, so the bit above the pier, was solid. Obviously, we didn't want to start cutting through the solid section because it would take a lot longer. The idea was to cut through the section that has the voids in it. Planning the slope of the cuts and everything else to make sure that we released the structures and we could get the piece out when we were done. And actually the sequence itself became quite vital when you started looking at it, particularly on the sections that were quite heavily curved. And then again, when we decided to preload and the amount we decided to preload to, it was all thought about and planned out. I think, yeah, it was 80% we said there, and then as the final cuts were being made, it would be adjusted on site to make sure it wasn't dropping. So the basic sequence was we dropped through the cores, and we cut through the outer web, and then we did the final cut through the inner web, and away we go. And the idea was to progress both ends at the same time during the works. And there you can see there a completed saw cut, and that is one of the tendons we're talking about there. You can see the duct is that outline there. Obviously that's concrete around it, bit of reinforcement, and then in here you've got grout and you've got the actual steel itself. Now you can see there, as that's been cut, it has retracted slightly, so maybe 1-2 millimeters. So you imagine these wires, these cables here, or these tendons here, are under a significant stress, and as you cut them, they have retracted slightly, but they have re-anchored, and you can see that because they've hardly moved, which is exactly what we said would happen, and it worked perfectly.
Sorry, and just to elaborate as well, one of the challenges we had actually on site with the 80% loading was the fact that the SPMTs they don't give you weights, they give you forces, and the forces are within about plus or minus 5%. And you can imagine the diamond wire we're using is only 8 mil, so literally, as we were cutting, if the bridge was to drop slightly, the saws would get jammed, and we had to kind of find a way to free them up. So that was a massive challenge on site.
I bet it was, yeah. I bet it was. How many wires did you break?
Don't know how many we broke. A few times we told them to pack up and let us bring the machines in though.
Just finish it off, yeah.
Yeah, I think to be fair, it was weird when we done the North Flyover, the one we had limited information on. We seemed to get it right most times, and the cutting was quite quick when we done the South. And again, I don't know whether there's anything to do with the curvature of the South, and obviously we had more of a crossfall on the South. But I think out of the 6 spans that we actually cut through, 5 of them got jammed. Yeah. Yeah. So, I mean, some of the cuts were due to take us 12 hours. Actually, took us 36.
Yeah, it's a big difference. So the SPMTs themselves, I'm not going to go into these too much because Tom will, but I'm just going to point out one thing on here. So on this drawing here, they've actually shown the power pack in the middle there. In reality, I think it would have been put off just at one side, and you can see there. So that would be the central props, and then the shear prop fit just here, and then the column itself would be, I'll do it in orange, would be sort of here and here. So that's the columns themselves, are sort of there and there. Hopefully that makes sense. So you're looking in plan. That's the arrangement. That's why the props were detailed as they were and had quite a narrow base on them, so the SPMTs could get on either side, and again the shear prop was. Need to erase that now, don't I? On top of the SPMTs themselves, we have to have a similar sort of beam arrangement, again, that picked up on the 4 webs. So again, we had a fabrication that went in place because the structure was on a cross fall and a long fall. These had to be specified for each individual location and was quite tricky, given you only had, I think, 600 mil stroke, isn't it, on the SPMT, Tom?
It's 500 operational. You can get a bit more out of them, but yeah, plus or minus 250.
We developed a scheme where we could try and use that as much as we could by bringing them down as low as we could with the stalls off either end, here and here, bring it into position, and then you could rotate those up. In practice, I don't think that actually worked out, that it was a bit too heavy, and I think you ended up packing them in place to get them up, generally speaking?
It depended, to be honest with you. It was a lot given on the platforms below, because we were just slightly out, 10 mil out on the platforms. We just didn't have the room to be able to rotate them up. But the ones where we did, I think quite a few of the spans, we managed to actually flip them on the pivots you put into the design.
So it works where the platform was bang on, but there really wasn't much room to play with. I think we had some of these. Best case, we had sort of 20 mil clearance to get through, and when you're talking about a structure that size, it's not a lot of float to play with. One of the more interesting parts we had was span NE and NF. Now, initially these were going to come out as individual spans, so that span there and that span there, but the stability assessment of the SPMTs wasn't very stable. This was pretty much the highest part of the structure, and if you can imagine looking at that SPMT there with a massive great 400 or 3 feet of concrete sitting on top of it, it doesn't look the most stable thing in the world. So the decision was taken to bring them out as as one section, so a pair of SPMT units underneath, and then we took this whole thing as one lump. So to do that, we had a steel beam that went on top and hung the decks below from them, and that steel deck span or steel beam span from SPMT to SPMT. Is if you imagine how that works at the moment, you cut the column out. This is trying to drop, and the post tension is also trying to pull it down. So we came up with this beam arrangement that sat on top here.
I think the other reason, sorry, Angus, was it was a sort of value engineering thing, because both those spans go over Byron Street, and the council were very nervous about having to close Byron Street on 2 occasions. So we looked, if you recall, we looked at it and decided we could actually take them all out in on one possession. So that also drove that. Okay,
so my memory's gone wrong there. I thought it was the stability thing that drove it, but that makes sense as well, to take it in one, and that's what we did anyway, wasn't it? It came out in one piece, yeah. And this is it in action here. You can see there the saw cut's been completed either end there, and can't really see it there. And I think they're starting to roll. Yeah, they are moving very slowly there. If you watch, you can see that section rolling out. You can see on top here the beams that we talked about with the little wires sticking up of the divvy dags that went through. You can also see there they've put in a empty deck unit to tie these 4 SPMTs together to make sure they operate as one unit. And you can see some of the big Lego kit that Sarens have for making up these jacking arrangements, support arrangements here. And you can also see the stalls we talked about there. It is moving very slowly, so I will fast forward a little bit as long as my except I've lost the control. Why is that? What's going on here? Sorry, I don't know what's going on today. I'm not having the best of luck with my computer today. Should have stuck to Google Slides rather than PowerPoint, shouldn't I? There we go, that's what I wanted, right. So there you go, I've just skipped it on a bit now. You can see it's driven out sideways. And if we skip it on a little bit more, there you go, and it's about to do its party trick, or one of the party tricks of an SPMT. You see the wheels turning there individually? Or sorry, not individually, be those 4 and those 4, those 4 turning. So it's all synchronized and turns together. You can see all the wheels have now turned through 90 degrees. You can see the power packs on the top there and there. And now it's starting to move off in the other direction. And away it goes. You can see the stub of the column there that we cut through. So that was quite a nice to see that happen. I think it was Richard standing in the pin ring video for me, but it was nice to see it anyway. You can see there, as we talked about, the voided sections again. And you can still see some timber form, and there you can actually see where the form was blown again, just there, where there's extra concrete on the structure. But that was a big moment for us all when that span came out. Could have had nicer weather, but such is life. And you can see again there the prop and some dodgy videos. Once they were cut free, they were taken over to a processing yard where we used another bit of Sarens kit, the SAR lift. Again, I'm not going to dwell on that too much because I think Tom will be covering it in a bit more detail. That is what a SAR lift is. It's a big gantry system with a jacking arrangement in here. And this one can lift, I think this is the SAR lift 2500, isn't it? 2,500 tons?
250 tons a column.
Oh, so it's the SAR lift 1,000, this one then?
Yeah, effectively.
1,000 ton altogether. That this could lift, and we were lifting about 650 was the worst case, I think. You can also see there a piece that's been cut up. So that's an SPMT sitting underneath it, just about to lift off that deck piece. Then the SPMT drives out, then it gets lowered down to the ground. Once you get it down on the ground, you've got to figure out what you do with it there. And the plan was to cut it into pieces and take it off site. We came up with these grillages. So the steel beams were brought down from a site Sam Evans have up in Scunthorpe. So again, the steel beam we used on top of NENF came from, was reused from a site in Scunthorpe, as were these. So we developed a system where have these beams and you notch out in the position where you're going to run through a track saw to cut them up. So that's one there being lifted into place. Put a series of those on the ground, and then you drop the concrete section onto it, which is what's happening there, and you cut it along those lines there, there, and there. And then you cut it the other direction into pieces that we can lift just like that with a big crawler crane and onto the back of a wagon and away. Now, originally, the four most easterly spans of the north and the south were going to be taken down with SAR lifts being put up in place. However, we had some issues with a cadent gas main that we just couldn't get approval to set the SAR lifts up on top of them. So that drove a methodology change to using more traditional means of demolition, which you saw at the back end of the video. So the final four spans of each, the north and the south, were taken out mechanically. As you can see here, working from one end to the other. Again, it all worked nicely. We propped them at third points and propped the columns, and then let Sam Evans get to work with their dirty great shear and munchers and smash it to smithereens. And that is what they did. And the works were completed successfully in December 2019. And it was a technically complex project in a very restrictive site. And it was all done safely, on time, on budget. And it was a collaborative scheme, just from even just the three of us here. But then you also had Graham's, the traffic management team, and you had Amy themselves, you had Core Cut. Between all of us, it took a lot of effort to get this job over the line and done in the timescales available, and to do it in a professional manner as we did. It was a cracking project to be involved with. Now we're going to hear from Jordan, who's going to talk us through some logistical challenges. Okay.
Finish your screen, please.
There you go. Bloody hell, have I gone on for that long?
You've had a good chat.
Bloody hell.
Can everyone see that okay?
I apologise. It only took me half an hour before. I seem to have gone on a lot longer today.
Yeah, we can see your screen fine, John.
Yeah. So basically, reason I picked logistics was behind the engineering. I thought that this was the biggest constraint. I know there's probably people on with us now. We've worked with S7s in the past, and we specialise in this sort of infrastructure and bridge demolition. But usually you're out in the open in a farmer's field over the rail, or you're on the middle of the M6 on a Saturday night. But this one was obviously a bit different, a different kettle of fish. I'm sure there's people in there who worked in the city centre as well. But I'll flick through this anyway. So I've basically broke this up into the external, which is the getting in and out of site logistical challenges, and the internal, which is how we had to get all this equipment working on site to the engineering sequence. So obviously the main challenges for us it would be the busy city centre environment. The main roads, the access roads, so I'll go touch on it more a bit later in the programme, but basically the Mersey tunnels, the M62 kind of all merged here as a sort of hub. You had Liverpool Royal round the corner, so two of the main roads were blue light routes, and then it was just a case of you had JMU surrounding it, you had the museum and library surrounding the site, and basically we had to close one of the roads that was the only access for staff into the library, museum and the emergency access route. Our compounds were all local car parks. We had a few local businesses that were affected by them, which obviously weren't happy. And ultimately, the main contributor to all of it is the equipment we had to try and get in and out of the site. So, just to recap, you've got the North Flyover and the South Flyover. And then our traffic routes, we've got to the north, we've got the Kingsway Tunnel, takes you over to the Wirral, and we've got Liverpool Port, which is a busy port. East, you've got the main access into Liverpool, the M62, and that basically comes down Edge Lane, down Hunter Street, and this is kind of what I'm talking about, which we've got all kind of splits off towards the docks. To the south, we've got the Queensway Tunnel, which is, again, another Mersey tunnel that takes you over to the Wirral. And just above that, we've got Edge Lane. Now, Edge Lane was now the main road. Basically, the South Flyover used to take you over this sort of junction and down Edge Lane, which takes you down to the waterfront and the Strand. So then our neighbours. So basically, as you've seen before, we had three Liverpool John Moores University buildings. And the footbridge that crossed Hunter Street was the main access for the students from the city centre to the main tall campus, which is up to the north, which didn't help us as well. We had student accommodation on both sides, and we started the programme a week before freshers. So as you can imagine, we had new students coming to town, never been there before, don't know the area. And they've rocked up, and you can see from Angus's presentation just like what was going on there. In the middle of that, we had a residential building that basically backed onto the flyover. Then we had two of Liverpool's landmarks. We had the International Library and the World Museum. And I've got a picture just in a minute which just kind of puts into perspective how close we are to all this. And then Dale Street. So anybody who don't know Liverpool, Dale Street's basically a road which is full of offices, pubs, restaurants. So it gets quite busy, particularly at weekends. So there's just a picture. This is looking towards the M62 to the east. So as you can see, I don't know if you see else, but you've got the library and the staff car park. You've got the museum, and then you've got Liverpool John Moores. So this picture was took a few weeks into the programme, so you can see just here is where the footbridge did once go, and basically that linked to this spiral staircase underneath the flyover. So at this point we had took all pedestrian access across this road, which comes off the 62, away from the students and any other public. And then just on the opposite angle then, you can see we've got the student accommodation, we've got the sports science building, the IT building, more student accommodation, and then this was a live office block, and then down Dale Street. So you can see the pinch points we had where the structure was close to the properties. And one thing that away from logistics, one thing that we really struggled with the museum was because of the obviously the stuff that they got into the museum, they had their own set of vibration limits, which was heavily dictated to us where and when we can't move around them. So we identified basically 3 compounds. Now these 3 compounds we took over memorial gardens, which had a couple of statues in close to the university, a car park. This was the existing footbridge, and then this was car park and a bit of green area, and then this one was a car park again. Now when we say these were the compounds, and you'll see from the pictures through the presentation, these were just basically the areas we could have permanently through the works. And what we basically had to do was take different areas as we move through the stages of demolition for exclusion zones and working areas, and give them back so as not to disrupt the local roads, the pedestrians, and basically all the local stakeholders. So again, the equipment that we had to get into site, and Tom will probably be able to confirm this, but off my memory, we had the 2 sets of SBMTs. Now, I think they come in about 20 loads with the associated steelwork. We had the SAR lift systems, which I think were, again, similar. You had your 300-ton crawler crane, which come in about 5 or 6 loads. You had the 150-ton mobile crane that come in a couple of loads. Then you had our equipment, which was anything from 7-ton to 45-ton excavators. And when we switched to mechanical demolition, we had the 90-ton excavator there. You had access equipment, ride-on rollers, fencing, cabins, etc. And then to build the platforms, we needed to get 10,000 crushing to site as well. Now, initially, to get us going, we had to get the above in 4 weeks, which you can imagine was a challenge, working around this road network and working with the stakeholders, which I'll touch on in a minute. Then working progressively through the demolition as per the original sequence. Per span, we had an average 12 sections. These are about 6 to 10 metres long and 2.5 metres wide, and we could go from anything between 35 to 50 tonne. You had the crosshead and column. Again, the crossheads range from 50 to 70 tonne, and that basically depended on the cuts. And the column ranged from about 20 to 40 tonne, and that was the height. So roughly, you had about 350 to 500 plus per span. Then we had the challenge of when we were lifting across, due to the other demands on site and the site program, we had to reconfigure the SBMTs, reconfigure steelwork. So usually we only had the crane available to us at night to remove some of these spans to the store, but obviously Angus touched on before where we were actually storing these sections as they come off. So it was hard to pinpoint exactly when and how, weeks in advance as we normally would, what was coming in and out. So I think Angus used the same photo, but basically this was a typical section leaving the site to go to its storage area. So stakeholders in terms of logistics, well, obviously with the weights of the loads, highways were heavily involved. We had to put movement orders in, mostly Cat 2 movement orders. So these were on 3-day notifications, but again, this was down to why we had to plan this. We couldn't just turn up with a wagon when we were ready. This had to be 3 or 4 days in advance, if not longer. The road closures, so this was the main closures of Hunter Street, Byron Street. We had numerous meetings and obviously a big dialogue with the local council, emergency services, and as well the public. Lane closures, so away from the major closures, we had multiple lane closures, and this was basically to give us the sufficient room for exclusion zones once we started cutting. So if you wind back to Angus's presentation, when we went from J&K and E&F, we had G&H that stood there. Now the props that went around G&H protruded into the road, so basically for 3 or 4 months we had to have a single lane closure, and that basically had to move on all the time. We had to keep giving areas of compound backs as we move through the demolition sequence. Another key, or another headache, should I say, was the library and the museum. Obviously that road, Keordon Street, which you'll see in a minute, was their only access for the staff and for the emergency services. So they were kicking up a bit of fuss when we had to say, due to health and safety grounds, that we've got to close that road. And then what I touched on before was once we took this footbridge away, that footbridge really gives students difficulty of crossing their major roads. And I think one of the diversions we put in place for the pedestrians was about a 20-minute diversion to take them around the site. Now, obviously, we were doing this in the winter months. You can imagine that students weren't very happy, but there's physically nothing or anything we could do about it.
It was more the local characters there, Jordan, wasn't it, that weren't happy?
Yeah, well, as you imagine as well, city centre, Dale Street, lots of pubs. We had a few issues with, what can I say, some intoxicated people still thinking the footbridge was there when it wasn't. That happened on a couple of occasions, so it was quite a challenge. So how we communicated with the externals of the site, we had letter drops, and that was letter drops to mostly the residents just behind the tall JMU building. There's a estate, and then you had the residents that were kind of sandwiched into all of it. And basically we had a few drop-in sessions for the residents and the stakeholders. A big thing that was pushed from the council, which good or bad I don't know, but a big thing that was pushed on them was transparency of what we were doing, to a point where a lot of our method statements were actually sent or made available to the locals. Whether or not they needed that information, I don't know, but that was one thing that we did do. But what we done was basically done some nice 3D sequencing from Angus's drawings. So people who didn't have a construction background could try and visualize what we were trying to do. We had public announcements, so I think every electronic sign in Liverpool was displaying when we had these major road closures. We had announcements on the radio, online, newspapers, some again which didn't really help us, but we had to just get on with it. Then we had the weekly TM meetings, and that was for all stakeholders. So involved in them meetings, you had Mersey Travel, Arriva buses, Graham's, Sarens, S7s, the council themselves, police, the fire, the ambulances. Just basically, I think we had about 35 people sat in that room, each with their own agenda. I think the most problematic to us was the buses, who claimed that we were going to shut Liverpool down to the people. But this is just all the people that we had to try and appease to get this, basically to get the ball rolling with the project, but then to actually get it finished. And then prior to that, we had the weekly TM meetings with our contractors, and that was more to discuss what was coming in our site, how we were going to go about it. I mean, at times we used the storage site as a holding point for wagons and cranes. We used our yard back in Widnes, 12 mile away, for a holding point. So it was just basically well thought out, but I'll be honest, it was very reactive as well. Now, the key priority in all this was the key dates that Liverpool published to the public of when we were shutting these major roads, and that basically throughout the work dictated what we were doing. So then I'll touch on the internal logistical challenges. So when I say internal logistics, I mean actually getting in and around site, on pedestrians around site, but mostly how we took these spans out and got them to the end product. So as you've seen from the pictures, we had this large scale blue equipment that just rocked up. Most people had never seen this equipment before, so I think it was quite of a shock once we started getting established actually how much we had tucked into this small space. Now again, because we had the compact schedules and the compact compounds, we couldn't just bring any equipment like we could in the field out to site to speed us up. So we had to, the crawler crane, I don't think stopped during all the work, but he basically had multiple activities that he needed to run concurrently. That needed to be constant dialogue between myself, who was actually on site, Sarens site manager, and Cork site team. Another one with that as well, which was a shock to us, but we never really got told prior, that once we started to take some of these spans away, we had to give back parts of the compound for the pedestrian routes. So there was a lot of double handling, a lot of digging up compounds to move fences in and then putting them back where we needed to. It got a bit of fun, to be fair. And then one thing that come out of the engineering was, because of the different heights, weights, that not every span could go. So with the SAR lifts we were using, we couldn't basically take any span into any SAR lift. They all had different SAR lifts that they had to go into, and each SBMT had different steelwork setups on top for different spans. So we had to really plan on when we were releasing SBMTs to be reconfigured and which SAR lift they were going into, which was probably the biggest headache out of the lot, and took many sheets of A4 paper. So you can see, just this is before the site come up to site, but you can see sort of the compounds just getting set up here. You've got the crawler crane on site, 2 sets of SBMTs, and I think a 130-ton crane. And then you can see when we were in full swing, just exactly how much room we had. So this was the first piece to come off. We've got a SAR lift here, 300-ton crane, telehandlers, 50-ton machine, MUP, cabins, mats. So you can start to get a bit of a feel of how compact this was. This is a 400-ton crane. You can see you've got a substation, the main structure, footbridge, museum, and just it kind of, when you look at pictures like this, it kind of makes it as surreal as it was to see actually what plant and equipment we managed to squeeze into Liverpool city centre. So how did we manage the internal logistics? Well, we basically, it was my job as sort of Graham's subcontractor and to take into consideration what Sarens, what we were bringing in, and what Corkut were bringing in that week, and put that into a bit of a load chart. And this is where, when we had the holding locations, etc., we had to communicate that back up to Graham's, who went on to communicate to the council, and then we had to pass it back down then to Sarens, Corkut ourselves, of when we can bring this stuff in. We had the daily, weekly meetings between the management team on site, just to make sure that we wasn't missing anything. We had daily briefings with all the site staff, because basically, as you could see from the compounds as well, I don't think you can clearly see from any of these pictures, but basically, if you look at this one, when we were in full swing, we had SAR lift here, SBMC reconfiguration area, and then this is our only access to bring deliveries in. So you can imagine we had to coordinate through various teams that Sarens had on site and our teams to let them know when there was a delivery coming in to free the crane up, and to make sure that we could safely offload the equipment and somewhere we could actually put it. We had the effective TM plans in place prior to rocking up onto site, and they were constantly reviewed. As I said, once we were moving through the demolition, the exclusion zones, we had to exclude 2 spans for every 2 spans we were cutting, so we couldn't go into them areas. So basically, we just had to be proactive, moving through the works to make sure that we had adequate storage areas and we could get equipment once it was finished with off-site straight away. And I think for me, the main reason why all this was achieved was just basically the work ethic we had through us, Sarens, and Corkut. As much as it, I'd say, get heated, we didn't get heated once, but we were very, very approachable with each other. And I think that is the key to all of it, is the fact that we work with each other. And for example, if Sarens had a delivery coming in that meant that S7s had to stop working, S7s would help offload the Sarens equipment to get that delivery out on site. And we all had smiley faces. And that's about me done. So Tom, I shall hand over to you.
Thank you very much.
I had a grey hair before we started this, though.
Right, so I'll share my screen, hopefully.
I apologise again for waffling on for too long.
That's
still
all right.
got people listening, Tom.
Oh,
okay. People there still.
Okay, so just let me know. Can you see that okay? Yeah, good.
Yes.
Right. So yeah, Angus has asked me to join the webinar today to talk to you about a bit of the aspects of Sarens scope. My background is I've done nearly 25 years in the construction industry. I started with a brief spell with Molam as a graduate civil engineer on site. I then moved on and worked for a heavy lifting and temporary works engineering consultant for a few years, became chartered in 2000, spent about another 6 or 7 years working mainly as a structural engineer on heavy lifting schemes. I then moved into sort of more operational role, running and taking on challenging heavy lift contracts, mainly in the Far East, to be honest, but out of the UK, and often related to long span bridges. A lot of infrastructure was being built. Well, is always being built in the Far East, so there was work out there. And then we developed the business a bit. We got into heavy lifting manufacture, which we did out of China. So I got quite a lot of exposure to equipment design, hydraulic design, electrical systems, that sort of thing. So yeah, in my career, I've worked on projects, I think, in most parts of the world: America, South America, Europe, India, Middle East, Far East. But after 20 years with that organisation, I felt I was getting to the period where I should really do something different. And so 2 years ago, I jumped ship and I joined Sarens. So if my slide will advance, what are we? Our Sarens, people know us just for big cranes, and this is a big crane, yes, on the Affinity Bridge up in Stockton. You might know us for our really big cranes. This is the SGC 250, also known as Big Carl, which is on Hinkley Point. It can lift 5,000 tons on its main boom at 40 meters. If we stick the luffer on, we can still lift just over 4,000 tons at 40 meters and about 1,250 odd at 65 meters. So we've got some big cranes. Indeed, we've got four SGCs in the fleet. 3 of them will be in the UK later this year. This is the biggest though. We are family owned still. We've been going 60 years. We've got a worldwide presence. Yeah, we're not about renting cranes really. We're about giving, look at the problem, find the solution, and put the equipment in there. We've got an extensive box of toys to play with, and we do all our in-house engineering in-house. We've got a strong capability, and we've got a great team of operational guys. So moving on to the problem in hand, or the topic in hand, is Churchill. So I'm going to start really by talking about how we approach the engineering for the dismantling. We got involved in, just going to move something a bit so I can see a bit more my notes. Sorry, I'll put that there, and I can see it. Okay, so our first challenge was to disseminate the information for these 20 spans that we were having to dismantle. We had varying spans, varying weights, varying ground levels. As Angus touched on, not great as-built information. We had a fantastic point cloud model, but actually that's quite hard to interpret when you have a very tight program, which was, I think we started developing the project about 19th of June, really, in any anger, and we had to submit all the engineering by the first week of August. So we had 6 weeks to work through the problem for a start on site, mobilizing early September. So that is a sort of, I'm not expecting you to really read that, but you can see the blue spans, or the things covered in blue, were the ones we were due to lower in situ. The main driver behind that was that the ground levels around there were such that it was really not practical to put the SPMTs in to drive them out. It would also mean we were driving the sections down Hunter Street and across Byron Street, which was also not popular, would not have been popular with some of our stakeholders. The 612 sections in white were the ones we drove out and lowered with the SAR lifts. And I think the heaviest span was around 600 tons. The lightest span was 250. The longest was 30 meters, and the shortest was 12.5 meters. And our ground levels went from somewhere between 4.5 meters to sort of 9.2 meters. So, you know, there was quite a range of challenges there to deal with. So the first thing we had to do was identify the method we were going to use. There had been discussions from probably mid-May with S. Evans on this, and some concepts were drawn up, and there was I think from Amy's an idea floated around involving SPMTs, and that probably was a fairly clear way to start with. We also needed to think about what equipment we were going to select, and you know, we've got a nice toolbox of equipment. We've got something like 1,700 cranes in the range. in the fleet, ranging from small telescopics up to big ringers. In addition to that, we've got barges, we've got jacking systems, we've got gantry systems, we've got skidding systems, we've got strand jacks, we've got steelwork. So we have to think, how are we going to put that together in a way that best serves the project? So we do some first stage engineering. We come up with a concept, which we do some verification on. We verify that works with the geometry of the project. And obviously here we have 20 spans we've got to try and work around. And we need to think about our interface with the load, because that's quite important. Pickup points, spacing of pickup points on the load, introduction of load between the lifting system or the movement system and the load, and also the interface with the ground. So we did a few concept drawings, just showing a few options. This was an option we looked at using strand jacks. This was the first generation, should we say, of the SARLIFT concept, which was what we went with in the end. And this was looking at how we might be able to support the decks when we drove them out. First, then we have to think about, well, is that equipment actually available? Obviously, Sarens' business is to keep their equipment busy, and it goes all around the world. So we have to look internally and do some internal checks, make sure that if we want to use that equipment, it's going to be available in the period. And probably as important, clearly, we have to have stakeholder buy-in. If we're proposing a scheme that's just not acceptable to one of the stakeholders, and there's a valid reason, we have to accept that, and we have to go off and find a different solution. So once we've got stakeholder buy-in and we know that the equipment we're proposing in principle is available, we will get into the detail engineering phase. And that involves verifying the chosen equipment for the forces imposed, fairly obviously, defining our boundary conditions. That's environmental, so we're talking about wind speeds we're going to operate in. We're talking about slopes we're going to operate across. So when we drive our SPMTs, as Angus touched on, we have to consider the stability of the trailer for crossing slopes. We have to define operating speeds for the trailers, and so on. We also need to firm up on our interfaces. So we need to check that the ground loadings really can be achieved by some ground improvements if we can't meet the proposed ground stated ground bearing pressures. And we have to check that, you know, how we're getting hold of this deck is suitable, and you know, in line with the work that Angus did, we worked quite closely on that. So yeah, there's a few slides here of our drawings that we did. I think we did nearly 80 odd drawings for the project for the different spans. Each configuration of SPMT was different. We had to think quite hard on that, how we would minimize the reconfiguration between each span, because there wasn't a lot of time between taking a deck out and taking the next deck out. So we had to work quite hard to think of an efficient way to minimize the reconfiguration. And you'll see between these two slides, we've actually got the same we've got the same base configuration here, and it's above that level that we change with different packing arrangements. We then the NFNE span, which was the two spans that went over Byron Street on the North Viaduct, we had a special arrangement for that, where we had effectively two separate SPMT arrangements, but joined structurally with a spacer deck. That was yeah, another setup and another challenge. And I suppose something which I'll get onto, but you'll note here, this is a definition of how we want the site to set up the hydraulic suspension arrangement. So I'll talk about that in a bit, but the SPMTs have hydraulic suspension system, and we have to make sure we set that up in a way that will ensure we still have a stable move. Then we have our SAR lifts. This is the first sheet of, I think, a 3-sheet drawing detailing how the various bits of kit will go together to build the SAR lift system. this is a typical general arrangement of showing the interface between the SPMT arrangement with the deck on and the SAR lift. And Jordan touched on this, that certain SAR lifts could only have, we had two different SAR lift arrangements. This is the same one actually. We had one that was freestanding. I've got a couple of photos later. The two towers were freestanding and they were propped in both directions down to the ground, and the other one had portalized in one direction and propped down to the ground in the other direction. And we could deal with different heights of SPMT deck arrangement on those. So that had to be thought about a little bit in the logistics. And this was the plan for the in situ lowering. I think there was quite a lot of work that would have been needed and was started before it was the scheme was abandoned, mainly because of the gas main, to get the ground levels, because the ground really did fall away. I think this was effectively over what had been a sort of rockery park area. I mean, park in the loosest sense of the word park. I think it was more a hangout for the ne'er-do-wells of Liverpool, but that was all cleared, and then the level was going to build up quite substantially here. I think there was something like 2.5, 3 meters of fill going in this point. And then of course,
I think the most we put in.
Was it 4 meters? Yeah.
Yeah.
And then, all the drawings are backed up by calculation notes, which went for both internal and third-party review. So once we've got the third-party review, once we've got all that done, as an engineering team, we've got to hand that over to the execution team. So there's obviously a handover. We get together with our operations team and make sure they understand what's going on. And we have ongoing engineering support on site. So we had an engineer from the team actually on site on Liverpool the whole time. There's a few photos I found off his phone of various things he'd done during his time there. Anything from just verifying a change on site, inspecting when the SAR lifts were assembled, answering questions from the operations guys how things get assembled. It's much easier if you've got, on this sort of project, if you've got somebody who really knows the scheme on site who can provide that technical backup, rather than the guys having to ring back to the office and try and get hold of somebody. And that's how generally Sarens work. So I'm going to talk about the equipment we used and give you a little bit of an insight into it. So our SPMTs are KMAG K24s. For this job, we use the latest generation, which is called the ST. Now, the ST has a payload capacity of 43.5 tons an axle. And when I talk about an axle is 4 tyres effectively, or 2 swing arms. So across those 4 tyres, we have a payload capacity of 43.5 tons. The tyres are PU filled, so you don't have issues about having punctures and blowouts. The width of the transporters are 2.43 meters, and the axle spacing is a standard 1.4. So if you bolt another one on, it's 700 mil from this axle line to the bolt plate, and another 700 mil to the next one. So you can bolt them end on end, and you can maintain your nice 1400 mil axle spacing. Our deck height we can adjust. The sort of neutral position is 1500 mil, and we have an operational movement of plus or minus 250 on that. We have a bit more, but we keep it within plus or minus 250. We use that not only to set levels and do things like pick the load up. We can drive in and we can then pick the load up and drive out. We also use that so that we can account for cross falls, long falls along the length of the SPMT by adjusting the level of the deck, which the operator has control over. So an SPMT is effectively a nice big structure with a very strong spine beam, which we use to move heavy loads. Part of the engineering is to check the forces in that spine beam to make sure that we aren't imposing, and the connections, we aren't imposing forces beyond its capacity, but it has an enormous bending capacity and shear capacity. So unless you get very, very long SPMTs, it's not normally a problem. The suspension is quite interesting. So each pair of tyres is on a swing arm with a hydraulic cylinder. We can join those cylinders together to group pistons, and that means that we basically have a pool of oil. So we have a pool of oil which is connected to all of these cylinders, and we have to link those different suspension cylinders together in a way that basically forms typically a three group support, so three point support. And then when we're checking our engineering, we have to ensure that we maintain the center of gravity within the triangle that is marked out by those 3 points. And we have to do some spillage checks. And there's a little video here which may or may not work. Sorry, I'm having a... There we are. There we are. So this just sort of explains how, so the oil in one cylinder, once we've set the system up, it's effectively a closed system. So you push up in one cylinder, another cylinder goes down. However, the operator does have the ability to adjust the level up and down by pumping more oil into that group or out of that group from the power pack. But as you drive along, this little video shows you how the wheels will automatically lift themselves up and over a bump. However, the deck, if you notice, the deck does take a slope. Now, the operator can adjust the deck as he passes over to maintain level. It's I think the point I'm trying to get, it's not a fully automatic system. Some people think you can tell the SPMT to stay level and it will just drive around the site and maintain a level deck. It won't do that. It will pass bumps, as the video showed, and take those out, if you like, within the suspension system. But the deck level has to be adjusted by the operator to keep it within the constraints prescribed by the engineering. This is a nice little video that shows how the steering on the steering on these SPMTs works. Each wheel or each axle swing arm is effectively individually steered. So we can crab. This isn't quite neat. We can carousel. So we can turn on a point. We can turn about the back on an arc. We can turn about the front on an arc. When the SPMTs are assembled together from their various components, as in blocks of SPMT axles, the operator will put into the control system the centroid of the SPMT where he wants to rotate about, and from that, the control computer knows when he selects the steering mode what to rotate about. So typically, there's multiple SPMT lines carrying a nice big module. You can basically put the load straight on top of the deck of the SPMT with a bit of packing, or you can do something a bit more interesting. You can combine it with some steelwork like we did in Liverpool to drive decks in or drive decks out. I think these are all installation photos. Or in fact, mostly using similar equipment to that we used in Liverpool. Or we can do some interesting stuff. We're moving concrete bridge structure here by an SPMT, some timber packing, and effectively a little cantilever system that picks up on some ledger brackets that have been cast into the side. So that was all part of the planning of that project. And here, in fact, we are moving a nice bridge in Paris, where we are using the bridge to help stabilize our transporters. So this structure is effectively a pin onto the top of our transporter arrangement. So we're sort of portalizing across the deck, and obviously that puts forces into the deck, which had to be part of the integral design of permanent works. So SPMTs at Churchill, and quite a couple of nice photos. This was one of the lower decks where our basic arrangement of SPMT and modular beam with just some packing allowed us to take out one of the lower spans. This is one of the higher spans, setting up one of the higher spans where we had to reconfigure the packing from a brace tubular system using our bracing system, which is just a kit of Meccano parts really. And here's a nice, hopefully it's playing well, video of one of the trailers coming. You can sort of see the operation of the suspension as it goes over things here. And you can see as it steers round, the wheels take different angles to as you would expect, because every axle has to steer a slightly different angle. So that's everything I was going to tell you about SPMTs. I'll talk a little bit about our SAR lift. So our SAR lift we used had a 250-ton capacity per column. It's a tower with a 1 meter square base, and the tower elements are typically 2.5 meters high. And within it, a hydraulic jack will climb up on a 500 mil increment. So there's hopefully, again, this will play a little video showing typically how we use it in a gantry configuration. We quite often use it for offloading components that we're delivering inside a building, and then we will use it with a skid system to move that whole component to its plinth. Perhaps it might be a generator or something. But you can see hopefully the cylinders in here which climb up the tower, and effectively we put a head beam across, and then that's slung to the load. And this is how it works. So if it's yellow, it's either moving or it's unlocked. So we start off and we have a base anchor, a hydraulic cylinder, a top anchor, and then this is our lifting beam. We start off, we unlock the top anchor. It locks by two shear plates that go out sideways into a key in the inside face of the tower on two sides. So it's unlocked. We extend our hydraulic cylinder until we get to our 500 mil stroke. We then engage our locks here. We do a short retract, which then transfers the load from the base anchor locks onto the top anchor locks. That means we can retract the shear plates within the bottom anchor, retract the cylinder to lift the bottom anchor up the tower, and then reinsert the shear plates to lock the bottom anchor and repeat the process. So it's a mechanical sort of locking system, quite efficient, quite fast, and relatively easy to set up and move around between sites. This is a sort of real life version of what you saw in the little animation, delivering a part of a power generation system in Turkey, I think, or Egypt. So typically we actually brace SAR towers together to form a sort of self-contained gantry. This was different to what we had to do in Liverpool, where we actually had to brace the SAR tower, sort of freestanding SAR tower, effectively back down to the ground to some kentilage to stop the thing, to provide the stability sort of thing falling over. And we also had to, we've got 250 tons come down here. We have to spread that load into the ground. So we agreed with Graham's through S. Evans what ground bearing pressures they could achieve by building us some nice pads, stone pads, which they did, and then they put a nice good layer of sand and compacted it and leveled it for us, so we could just put our load spreading mat straight onto there and build the SAR lift off. That's a photo during assembly. you can see we have to slot our lifting beam down between the towers of the SAR lift. And then that's one of the SAR lifts. You can see here we're braced in both directions. The lifting beam, this allows actually lifting beam to go much higher because it can effectively pop out the top of the SAR lift, and that's why we had to have one like this, because to deal with the higher sections. And our other SAR lift arrangement was portalized. One of the reasons for this was the tight site constraints. We didn't want another load of bracing, which would have completely isolated this area of the compound and this area of the compound. So it was braced in the longitudinal direction, but transversely it was stabilized by portalizing it. The disadvantage of this was the lifting beam couldn't go any higher than there, which did limit which of the higher spans we could take in there. I'll very quickly, the other option we looked at, I know time's going on, so I'll rattle through this, was strand jacks. We did look early days about putting 485-ton strand jacks on towers, but we concluded that it would not be as efficient and it would take up more space in what was a very constrained site. I think I'll skip that, bearing in mind the time. So just a bit about our jacking systems. So in addition to the SAR tower, which climbs up, the SAR lift, in which the hydraulic cylinder climbs up inside the tower. Another option we have in a toolbox is various jacking systems. This is a new one we've just developed, has just been tested, which is a bottom feed system. It's neat. It can do 350 tons a tower, and it can jack freestanding up to 6 meters, and it can jack beyond that by putting in a bracing system. I put this in because this is our next challenge with Angus and Jordan, which we're just getting ready for, which is a job we're doing in Leeds. I must say Leeds, not Liverpool. I get the two muddled up because they begin with an L. The next job after that we're going to do is London, guys. All right, we're going to keep on the L. So here we are taking out a bridge using a jacking system, which is 250-ton capacity tower. It's a top-fed system. Typically, we use it actually to lift bridges up off their pre-assembly position up to height, and then we'll bring in some SPMT. So here you can see a bridge, well, understood outside the bridge is there. We've jacked it from assembly trestles, and then the SPMTs have been brought in with a static support structure on it. Here's another move we did in Canada using actually SPMTs with the jacking system on it. And that is very similar to what we're going to be doing in Leeds next month, where we're picking, this is a bridge, 3-span bridge going through the centre of Leeds, carrying one of the trunk routes. That's being closed to refurbish, to remove and rebuild the bridge. North carriageway, south carriageway in 2 phases. And we're driving out the central spans on an SPMT arrangement with jacking towers. We basically drive it out from here, drive it about 50 meters. We'll then jack it down on the SPMTs. And the advantage of that is the SPMTs are spreading the load, so there are no special foundations required. We can jack it down on the carriageway, or with the SPMT sitting on the carriageway. And then we drive it off about 600 meters to a laydown area where S7s will make merry with it. I'm nearly there, so don't worry if you're getting desperate for the loo or a cup of tea. I suppose the only thing to say, what happened to the in-situ lowering? Nobody's mentioned that. Well, actually, I got caught out because it was mentioned, the gas main. I think the gas main was one of the drivers. The other driver, as I remember it, and you might correct me, guys, is the time it was going to take to set up the SAR lift at each position and all the ground improvements. And once the gas main became a problem, it was easier to push the client to say, look, we can't actually put these ground improvements in. Can we try demolishing one span? And that very quickly became demolishing all the spans. So that's what happened, really. The gas main, plus the program, once we learned how long the ground improvements are going to take. And I think, just to conclude, really, I think the project success was really between, the group was driven by the trust we had in each other. We were quite open. The teamwork we developed, I think, in terms of engineering organisations, I think we and Andun got a lot of trust quite early on, and we're quite happy to share our problems and talk openly about solutions, rather than sort of finding something and trying to bury it in a drawing somewhere. So we're very, it's all about trust, teamwork, communication, and openness in this sort of environment to get the project done as quickly as we got it done. Both you and I are pleased that that's all of it. I shall stop sharing my screen and